Nuclear chemistry. So far, we've talked a lot about the atomic theory. Specifically, Dalton's atomic theory says that atoms cannot be created or destroyed, simply rearranged. Make sure that you have these blanks filled in your notes. Next, I'm going to differentiate between chemical and nuclear reactions. On your note sheets, you should see two different titles, one for chemical, one for nuclear. We're going to write down 3 bullet points for chemical reactions. The first bullet point should be that atoms gain, lose, or share electrons in chemical reactions. So again, we're writing a little bullet point under chemical, and we are writing atoms gain, lose, or share electrons. The second bullet point under chemical is that atoms retain or keep their identities. If you don't like the word retain, you can use the word keep. Atoms retain or keep their identities. And the last bullet point under chemical reactions is that they release small energy changes. Small energy changes. So the 3 bullet points again: atoms gain, lose, or share electrons, atoms retain their identities, and small energy changes. Next, we're going to look over at the nuclear side. So again, 3 bullet points for nuclear reactions. The first is that they alter the structure of the nucleus. Alter structure of the nucleus. And just to remind you, in the nucleus there are protons and neutrons, so we are changing those numbers of protons and neutrons. The second bullet point, extremely large energy changes. And the final bullet point is going to be it affects the identity of an atom. And you may even want to put changes the identity of an atom. So again, to make sure you have all 3 bullet points for nuclear, they alter the structure of the nucleus, extremely large energy changes, and change the identity of an atom. The next important category on your notes is called unstable nuclei. I'm hoping you remember doing a simulation together called Building an Atom, where we were loading protons and neutrons into the nucleus and electrons and energy levels around the nucleus. Specifically, I hope that you remember putting more than 1 proton in the nucleus without neutrons and seeing that nucleus kind of bounce around. It was unstable because of the positive charges that were in it together. Neutrons are needed to maintain stability. They don't have a charge, they're only mass, and their role is simply to hang out in the nucleus in between those positive charges to make sure that the protons don't repel one another. Well, for this particular section in your notes, we're going to define 2 different things, and the first is called a radioisotope. The definition of a radioisotope is isotopes of atoms with unstable nuclei. Isotopes of atoms with unstable nuclei. So if I have a nucleus that has too many positive charges, that's unstable, it will end up gaining or losing some number of particles, and as a result, we're going to end up with a different mass, and typically we call those radioisotopes. Next up, we have the word radioactive decay. The unstable nuclei, in order to become stable, what they'll do is they'll emit or they'll release radiation. And I do want you to write down this word radiation and define it as high energy particles or rays. So radioactive decay is when an unstable nucleus emits or releases radiation to become more stable. As that nucleus gets rid of some of those high energy particles from the nucleus, it does get smaller, so we call it radioactive decay. A nucleus will continue to emit or release radiation until it becomes stable, and you'll fill in those blanks on this section as well. There are 3 types of radiation or particles that a nucleus will give off if it's unstable. The first is called an alpha particle, which we've discussed before. The second is a beta particle, and the last is gamma radiation. I want you to take a moment and fill in the important information you see on this table, including the symbols. Look, the alpha particle, the symbol kind of looks like a cursive A. For beta, it looks like a capital B with a long tail. And then for gamma, I almost like to think of that as a fancy lowercase y. The description. So really important, an alpha particle looks like a helium nucleus. It is 2 protons and 2 neutrons, so it has a mass of 4 and an atomic charge of 2. So for now, just copy that down. A beta particle matches the exact composition of an electron, so a charge of -1 and a mass of 0. And gamma rays are like photons. They don't have mass, they don't have charge, they're just very high energy particles. The charge of alpha radiation is a positive 2, beta radiation a -1, and gamma rays 0. Mass for alpha particles 4 atomic mass units, for beta radiation 0 atomic mass units, and for gamma rays 0 atomic mass units. For approximate energy, I just want you to compare the numbers that you see here. 5 versus 0.05 to 1 versus 1. And last is relative penetrating power. Alpha radiation, they're the biggest out of all the types of radiation, are blocked by paper. Beta radiation, which are very small, can be blocked by metal foil. And last, gamma rays are not completely blocked by lead or concrete. So they are only energy, they're very fast moving, and they are the type of radiation with the highest penetrating power. So you might remember Rutherford from our atomic theory unit. Rutherford did some testing where he was shooting alpha particles at gold foil, and he saw that some of those alpha particles deflected and changed directions. So he did another similar experiment where he took a radioactive sample, and you'll see it glowing there on the left-hand side. So here's my radioactive sample, and he shoots it in between a positive plate here and a negative plate. And what we see is that all of the types of radiation that are given off by this radioactive source, they end up splitting. So this says over here on the right-hand side, what conclusions can we make based on the size and deflections of the radiation? And the first thing I want you to look at are the directions of the deflections. So this blue line represents beta particles. And beta particles move up towards the positive plate. And we should know at this point that opposite charges attract. So because a beta particle moves up towards the positive plate, it must have a negative charge. Same with our alpha particles. The alpha particles move down towards this positive plate, or towards the negative plate, sorry, so they must be positively charged because opposites attract. So one more time, let me erase my drawings here. Beta particles move up towards the positive plate. This must mean that they're negatively charged. Alpha particles move down towards the negative plate, so they must be positively charged. And last but not least, we have gamma rays. They actually don't deflect at all, they just go straight through. That's that black squiggly line you see. So I can conclude that gamma rays have no charge. They don't move up or down towards either of the plates, so they must not have a charge at all. And the second part of our conclusions can be about the size of the deflections. And you'll see I've got some blue arrows right here. I want you to compare the distance of the beta particle. How far did the beta particle go up versus the distance that the alpha particle went down? What I'm hoping that you're seeing is that the beta particles moved a larger distance, or were deflected a larger distance than the alpha particles. So the last conclusion that we can make is about the size of each of these particles. I like to give the analogy of carrying a backpack. If you're carrying a backpack of feathers versus a backpack of bricks, which one can you carry further because it's easier to move? And I'm hoping your answer is a backpack of feathers. So the conclusion that I'm going to make here is because the beta particle moved a greater distance or a greater deflection, it must be smaller in mass than the alpha particles. Because the alpha particles moved, they deflected, just not as far. So beta particles must be smaller in mass than alpha particles. Now for gamma rays, since they didn't really move, I can't really come to any conclusions about their mass, simply because they just went straight through. So our conclusion so far, beta particles are negatively charged and are less in size or have a lower mass than alpha particles. Gamma rays, currently we know that they have no charge, and alpha particles we know are positively charged and have the largest mass. We're exposed to radiation all the time. Which type of radiation should you avoid at all costs? By looking at the picture, it looks like alpha particles are blocked by paper, beta particles can be blocked by wood or a metal foil, and gamma rays can be almost blocked, not completely blocked, but they can be blocked by concrete or by lead. So this says, how does the size or mass of each type of radiation affect its penetrating power? And the conclusion that I want to come to is that the bigger the particle is, the less penetrating its power. So the bigger it is, the easier it is to block that particular type of radiation. So just to refresh your memory, the number of protons, or the atomic number, is the identifying characteristic of an atom. That's how we can tell who the atom is. So if an atom has 6 protons, I can look at atomic number 6 on the periodic table. I can see that it's carbon, and I know that I have an atom of carbon on my hands. What happens if an atom's atomic number is altered? Well, the identity of the element changes, resulting in the formation of an element that was not initially present. It's mutated. We actually call these transmutations, and it's one of the bullet points that you listed under nuclear reactions. So we said in nuclear reactions, the identity of my atom is altered. And that's exactly what's occurring here in a transmutation. In chemical reactions, we can't alter the identity of the atoms. We can alter how they're arranged with one another, but we can't alter the structure within the atom itself. So let's look at transmutations and try to determine when they occur. The number of neutrons needed to maintain the stability of the nucleus is critical. So remember, the nucleus houses protons and neutrons, and if we have too many positive charges together, that nucleus is going to start to decay. It's just too many positive charges. For atoms with an atomic number less than 20, a 1-to-1 ratio of protons to neutrons is sufficient. So for every 1 proton, as long as there's 1 neutron, that is enough neutral charges in there to keep my protons from repelling one another. As the number of protons inside the nucleus increases, so as the number of positive charges inside the nucleus increases, more and more neutrons are needed to maintain stability. Eventually, no number of neutrons will suffice, and protons will need to be released to maintain stability. So eventually, you can't have that large of a number of positive charges. No number of neutrons are going to be capable of maintaining stability. So in this case, my nucleus is going to start to get rid of some of those positive charges in order to maintain stability. This is when it emits radiation and it mutates into a different atom that was not there before. Lead, with the atomic symbol Pb, is the last stable nucleus on the periodic table. Any element with an atomic number greater than 82 will decay spontaneously. So that means if there's more than 82 protons in the nucleus, your nucleus will start to spontaneously emit radiation to get rid of those extra positive charges until that nucleus becomes stable. So let's take a look at each type of radiation again. These are the particles that your nucleus will give off in order to become more stable. The first is beta decay. During beta decay, a very fast-moving electron is emitted from the nucleus. But where did that little guy come from? So here's what I'd like for you to write down for beta decay. We know that electrons do not exist in the nucleus. Electrons only exist in quantized energy levels around the nucleus. So where did that electron come from? And the secret is a neutron. A neutron is converted to a proton by releasing a negative charge with no mass, which is the definition of an electron. So let's see if we could break this down a little bit further. We have a neutron. What we know about a neutron is that it has a mass of 1, and it's a neutral charge. 1, atomic mass of 1, neutral charge. Well, for this neutral charge, we're going to say that that neutral charge is a result of a combination of a positive 1 and a negative 1 charge. If I take +1 and -1 and I add those two numbers together, I get an overall 0 or neutral charge. So what were to happen if this neutron gives off this negative charge? If it goes away, releases it from that nucleus, what I end up with now is still a mass of 1 on the top, but now instead of a neutral charge, I have a +1 charge there at the bottom. And by definition, a mass of 1 and a charge of +1, that's a proton. So what has been emitted? No mass, and a negative charge, hey, that's the definition of an electron. So under beta decay, we're going to put a neutron is converted right here. A neutron is converted to a proton by releasing a negative charge with no mass. The only other thing that I want you to write down about beta decay is how the emission of a beta particle affects mass number and atomic number. And we're going to do that by analyzing what you see up here. And I'm going to add in my beta particle has a mass of 0. Uh-oh, that's not what I wanted to do. My beta particle, well, I guess I can get rid of it. Let's try again. My beta particle has a mass of 0 and a charge of -1. So it's identical to an electron. I want you to look at what has happened. If this was my initial nucleus over here, it has a mass number of 131 and an atomic number of 53. Look at what it has mutated into. First of all, it's a completely different element. My mass number was 131 to start, and now look over on the right-hand side. It's actually still 131, so the effect on mass number is none. It stays the same, and that's because a beta particle also has a mass of 0. Now look at atomic number. For iodine, its atomic number is 53. Now look over on the right-hand side. The atomic number is 54. So the effect that a beta particle emission has on a nucleus is that it increases my atomic mass, or I'm sorry, my atomic number by 1. Atomic number increases by 1. One last thing before I move away from this slide, I want you to look at both sides. So let me try to get rid of some of my bonus stuff over here. And let me rewrite in that 0 and -1. What I want you to see is that the mass numbers and the atomic numbers on both sides should be equal. So on the left-hand side, I have a total mass of 131. Now I want you to look at the mass numbers on the right. So I have 131 plus 0, which is still 131. Now let's look at atomic number. I have an atomic number of 53 on the left, and on the right, 54 plus a -1, and that's equal to 53. So atomic numbers and mass numbers should be equal on both sides of a nuclear reaction. Next up is alpha decay. I want you to write down for alpha decay that it is 2 protons and 2 neutrons emitted from the nucleus. 2 protons and 2 neutrons emitted from the nucleus. I also would like for you to write down that alpha decay is needed for very heavy nuclei. 2 protons and 2 neutrons are emitted, and it's needed for very heavy nuclei. So we're talking very bottom of the periodic table. Way too many protons, we need to get rid of a bunch. Both numbers of protons and neutrons need to be reduced. Let's take a look at this and let's do a little analysis here. What do we currently know about protons? We know we're releasing 2 protons, so let's try to figure out what that's going to look like. I know protons have a mass of 1 and a charge of +1. So if I have 2 protons being released from the nucleus, that's a mass of 2 and a total charge of +2. But we're also releasing 2 neutrons. Right here, this is 2 neutrons. So what does that look like? Well, I know neutrons have a mass of 1, but no charge. So if I have 2 neutrons being released, that's a mass of 2 and no charge. So what is the total mass and total charge being emitted or released from my nucleus? Well, I'm going to add my numbers here. My total mass, I have 2 coming from the protons and 2 coming from the neutrons. So total mass being emitted is 4. Now let's talk about charge. I have a positive 2 coming from the protons and 0 coming from my neutrons. So the total charge being emitted from the nucleus is a positive 2. And what I want you to see is that an alpha particle matches that of a helium nucleus. 2 protons and 2 neutrons with a mass of 4, and an atomic number of 2. Now let's do a quick analysis here of the effects on mass number and atomic number. So we started out over here with radium, radium-226. So when you see that dash 226, that means its mass number. The number on the top 226 for radium, its mass. Over on the right-hand side, let's look at the effect that alpha decay or an alpha particle emission. So this radium-226 is releasing that alpha particle. What does this nucleus look like if it releases 2 protons and 2 neutrons? Well, take a look at the mass number. It started off as 226 and now it's 222. So the effect that alpha emission or alpha decay has on atomic mass is it decreases or goes down by 4. I also want you to notice that 222 plus 4 is equal to 226. So my mass numbers should be the same on both sides. Now what about atomic number, which is probably more important in my opinion. Let's look at the atomic number 88. We said that an alpha particle has a +2 charge, so it is going to, if I release an alpha particle, look at the atomic number. We started out at 88, and now it's 86. So the effect that alpha decay has on a nucleus is that its atomic number goes down by 2. And then again, I've got 88 on the left, and on the right, 86 plus 2 is equal to 88. So atomic numbers are equal on both sides, and atomic masses are equal on both sides. A quick recap. If a nucleus releases an alpha particle, my atomic mass goes down by 4, my atomic number goes down by 2, and my nucleus is on its way to becoming stable. It's currently not stable. Remember we said lead is the first stable nucleus on the periodic table, and it has 82 protons. Now radium has become radon, but radon still has 86 protons in it. It still has too many. So this radon is still going to go through some kind of decay until it becomes stable. Gamma rays. Gamma rays have no mass, no charge, they're only energy and lots of it. And that's what I want you to write down for gamma rays. No mass, no charge, only energy and lots of it. So on this gamma symbol, I'm going to put a 0 on the top for mass, and I'm going to put a 0 on the bottom for charge. Gamma rays almost always accompany alpha and beta radiation and account for most of the energy loss. So we're just going to add here that they almost always accompany, and that's not the right color I wanted. Let's try again. They almost always accompany alpha or beta radiation. And you'll see here, you see how that this nucleus is emitting or giving off that alpha particle. It's also emitting 2 gamma rays. So gamma radiation typically accompanies alpha or beta radiation. What effect does the emission of a gamma ray have on mass number and atomic number? Well, if the mass number is 0 and the atomic number is 0, it has no effect on either one. The only thing gamma rays are is very high moving energy particles. Now we're going to try a little balancing of nuclear reactions. So when we went through the alpha, beta, and gamma radiations, we were looking at atomic numbers and mass numbers, and I showed you that the mass numbers on the left should be equal to the mass numbers over here on the right if we add them together. So same goes for atomic number. We're going to analyze the atomic numbers and the mass numbers and their changes when a particle is ejected. Your goal is to either determine what kind of radiation was given off. Was it alpha, beta, or gamma? What is the new radioisotope? So here in this example, we're starting out with radium, and once it emits this alpha particle, it mutates into a new radioisotope, which is radon. You see it has a different symbol than it had before. And the last type of question that you might be asked here is, what was the original radioactive nucleus? So what was the original mass number and atomic number if you know the new radioisotope and the type of particle that was given off? So let's look at the missing species in these 3 examples and see if we can figure it out. The first one, we have potassium, the letter K. It has a mass of 43. And we're going to look at each one individually. Let's look at just the mass numbers first, and then we'll go back and do the atomic numbers. So I have a mass of 43 on the left and a mass of 43 on the right. So this missing species, whatever particle that this nucleus has emitted, must have a mass of 0 to make sure that they're equal on both sides. Now let's look at atomic number. I have an atomic number of 19 on the left and an atomic number of 20 on the right. So in order for both sides to be equal, I have to have an atomic number of -1 because 20 minus 1 is equal to 19. So what kind of radiation has a mass of 0 and an atomic number or charge of -1? That is a beta particle, B. You may also see that written as 0, -1 with an E. And that is the same thing. So you can have the letter E for an electron or that fancy looking B with a long tail for beta decay. They mean the same thing. So we can describe this nuclear reaction as potassium mutating into the radioisotope calcium by emitting a beta particle. Example number 2, we have a uranium atom with a mass of 232 and atomic number of 92. I see that it has emitted an alpha particle over here. So what I'm looking for is the radioisotope. What does uranium mutate into after it emits or releases an alpha particle? I see that the mass number is 233 on the left and is 4 on the right. So if I want to figure out what that missing mass number is, 233 minus 4, I get 229. So the missing mass number is 229. Now what I'm missing is the atomic number, and I have an atomic number of 92 on the left. That was my initial nucleus, and when it emits an alpha particle, it loses 2 protons. So my atomic number should go down by 2, and my missing atomic number here is a 90. 90 plus 2 is equal to 92. Now this one has one more special piece because we have to figure out who this element is. I see that it has an atomic number of 90, so I'm going to look at the periodic table. I'm going to find atomic number 90, and I'm going to see that the symbol for atomic number 90, and that's a really small space, so I'm going to rewrite over here. We have a mass number of 229, an atomic number of 90, and when I check on the periodic table, the element with atomic number 90 is Th, or thorium. So this is the radioisotope that uranium has become after it emits an alpha particle. And the last one, I need to figure out who the original nucleus was. So in example number 1, we were able to determine the type of decay. It was beta decay. And example number 2, we were able to determine who the radioisotope was, the new nucleus that my original nucleus mutated into. And for example number 3, we want to figure out who that parent isotope is. Who was that unstable nucleus who emitted a beta particle in order to become more stable? And let's look at this example. This one is actually the easiest out of all. I see that I have a mass of 14 and a mass of 0. So the total mass over here on the right-hand side, and I'm going to write it over here again because that's a really small space. My total mass has to be 14. And the last thing I'm going to look at are my atomic numbers. So I have a 7 and -1, which means my atomic number should be 6 on the left-hand side. Same thing, I'm going to go to the periodic table. I'm going to find element number 6, and I'm going to write down its symbol, which is carbon. So my parent radioactive nucleus was carbon-14. Next up, we have decay series. So earlier we mentioned that any nucleus with an atomic number greater than 82 is unstable and radioactive, and it will decay. It will spontaneously start to give off these radioactive particles, alpha, beta, gamma, in order to become more stable. So to achieve stability, a nucleus has to discard protons. It also has to lose neutrons. So here's what I'd like for you to write down for decay series. It's a series of steps taken to achieve a stable nucleus. series of steps taken to achieve a stable nucleus. I also want you to write down that the final nuclide, which is the number of protons plus neutrons, or our nucleus, is usually an isotope of lead, and lead has the atomic symbol Pb. So that final nucleus is usually an isotope of lead. And then I want you to look at the graph over here. You'll see that we start out with this radioactive nucleus of uranium-238. And each one of these arrows represents a radioactive emission. So this first arrow that you see here, this uranium-238 becomes thorium-234. My uranium has emitted an alpha particle. It has become thorium-234, mass number 234, atomic number 90. So my uranium lost mass of 4, atomic number of 2. But that wasn't enough to make the uranium stable. So what we see is that it will continue decaying until it becomes stable. So after it releases this alpha particle, then it releases 2 beta particles. After that, we see that it is going to release 1, 2, 3, 4, 5 more alpha particles. With each alpha particle emitted, it loses 2 protons and 2 neutrons. So you see that the nucleus changes its identity every time it loses one of those alpha particles. Eventually, we reach an atomic number of 82, which is lead. And once we reach that 82, that uranium-238 that we started with is finally a stable nucleus, and it will no longer decay any further. So a decay series is these set of steps that a nucleus takes in order to become stable. Half-lives. So a half-life is the amount of time it takes for half of the atoms in a radioactive sample to decay. So if we start out, I'm looking at this graph here, if we start out with, it looks like 400 atoms in a sample, and this is sodium-24, how long of a time does it take for half of those atoms to decay? So how long, if I start with 400 atoms, how long before half of those atoms are gone? So half of 400 is 200. And what I see here on the x-axis is time in, and it looks like maybe that's hours. My graph is not super great. I can't read what that unit is, but we have a unit of time on the x-axis. So what this graph shows me is that after 20 hours, half of my sample remains. So I started out with 400 atoms, and after 20, well, maybe not 20, that actually looks like it's less than 20. I would call that maybe 15 to 18 hours. My sample has decayed by half. I have half of the number of atoms. Each radioactive atom has its own half-life, and the more stable the atom is, the longer that half-life will be. The only thing I need you to write down for half-life is what you see in bold, the amount of time it takes for half of the atoms in a radioactive sample to decay. And the last 2 slides I have for you are fission versus fusion. You don't have this on your note sheet, but we did create a T-chart in class. Nuclear fission is for a very heavy nucleus. And here's what I need you to know. I need you to know the difference between the words fission and fusion and examples of both. So fission means to break apart. For nuclear fission, one heavy nucleus breaks into 2 or more smaller, more stable nuclei. And you can see the picture here. So the first thing you're writing down for nuclear fission, and you either have a note sheet that you created, a sheet of notebook paper, anywhere you see some extra space, you've made a T-chart, you have fission on the left and fusion on the right. The first thing you write down about fission is a heavy nucleus breaks into 2 or more smaller, more stable nuclei. Very important that the 2 nuclei that it breaks up into are more stable. So here I have this uranium-235. It is a very, very heavy nucleus, and it is going to break into 2 smaller, more stable nuclei, krypton and barium. Both of these elements have an atomic mass and an atomic number less than 82, so both of these are more stable nuclei. The next thing I want you to write down about nuclear fission, so far you have heavy nucleus breaks into 2 or more smaller, more stable nuclei. You have large amounts of energy released. And I also want you to write down that these are used in power plants. So every power plant that you see, there's one behind our school that you can see smoke coming out of every morning on the way to school. They are generating electricity via nuclear fission reactions. And ultimately, the last thing I want you to write down or draw is the picture you see here. So I have one big heavy nucleus, and it's splitting into two smaller nuclei. Also notice this little blue guy. This is a neutron. So we start the chain reaction by hitting this nucleus with a neutron. It splits into two smaller, more stable nuclei, and it also emits 3 more neutrons along the way. So if you had to guess, what do you think these 3 blue neutrons can then do now that they are free? And the correct answer is on the next slide. I don't need you to write any of this down, but I did want you to see it. Each fission of uranium releases additional neutrons. Those are the 3 little neutrons we just saw. It creates a self-sustaining process in which one reaction initiates the next. So this neutron hits this uranium, it splits into 2. It also releases 3 more neutrons, and check out this neutron here. It goes and hits another uranium atom, it splits into 2, releases more neutrons. That neutron hits this uranium and it splits into 2 smaller and releases more neutrons. So what we have is a self-sustaining chain reaction, and that's exactly how energy is generated in nuclear power plants. The number of fissions and the amount of energy released can increase rapidly, so they need to be maintained and controlled so that explosions don't occur. There were some explosions in recent history. There's one in the Ukraine, in Chernobyl. There is one in Japan, and more recently there was a very small one in a small town called West Texas. The explosion of an atomic bomb or chemical plants like Chernobyl are a result of an uncontrolled chain of nuclear reactions. And last but not least is nuclear fusion. So on the right side of that T-chart, if fission means you take one big and you break it into 2 small, fusion means you take 2 small or lighter nuclei and combine to form a larger, more stable nucleus. This, in comparison to fission, releases an incredible amount of energy, more so than fission. So when you're comparing the two, fusion generates the most energy. Where can we find fusion reactions? Well, unfortunately on our planet, the only place we can find them is the hydrogen bomb. Other places, the only other places that you'll find nuclear fusion is the stars and the sun. And actually, the fusion reactions that are happening on the sun almost every second are what is fueling our planet. So those fusion reactions release incredible quantities of energy on the sun. They ultimately reach our planet, and that's how all of the energy that we have is generated. The awesome thing about nuclear fusion is that it produces very little, if any, radioactive waste, whereas in nuclear fission, it does release lots of radioactive waste, and we have to find creative ways to dispose of that waste. Nuclear fusion could solve the world's energy crisis because it does generate such large amounts of energy with little radioactive waste, but it requires such an extremely high energy to initiate it, a temperature of 5 million Kelvin, and we don't really have the power to initiate that kind of reaction and sustain it and ultimately confine it. We don't have materials on our planet that can sustain that kind of temperature without melting. So that temperature has been achieved using an atomic explosion, but it's not a very practical way to generate electricity or energy, so it's not one that we are doing currently. But if you can solve this this world problem, if you can figure out a way to perform nuclear fission reactions on our planet safely, and you can sustain them and confine them, you will be a billionaire for sure. One thing we briefly talked about at the very beginning of this unit were uses and effects of radiation. They have so many positive benefits, like radio tracers. They're used in treating cancer in multiple different ways via technology, medications. They produce an abundant amount of power. They help us date things that are very old. You've heard of carbon-14 or C14 dating, but they're also used as instruments of destruction. And what you see here is, I believe this is Hiroshima, and this was before the explosion on the top, and on the bottom was right after that explosion. It just generates an incredible amount of destruction. So there are pros and cons to both, and it's a good debate to discuss how to use nuclear power and radiation moving forward.